Every year, thousands of missiles are produced in factories around the world, driving a multi-billion-dollar global market. The United States and Russia lead this production, dominating a large part of the sector. But do you know how these complex and powerful devices are manufactured? In this video, see all the stages of missile manufacturing, from the initial design to the final product. A missile is, in short, a set of explosives embedded in a motorized and controllable vehicle. The name comes from the Latin verb mittere, which means to send. The missile industry emerged during World War II when German engineers created the famous V-2, the first long-range ballistic projectile. But it was during the Cold War that they became popular. They reached the 1980s and 1990s as the most important weapons, because of the relative accuracy with which they could hit a specific target thousands of kilometers away. There are several types of missiles. The main ones are cruise missiles, which fly at lower altitudes with constant propulsion and can be launched from various platforms. Hypersonic missiles, which travel at speeds greater than Mach 5 times the speed of sound and can perform maneuvers. And ballistic missiles, which fly in parabolic trajectories, with one propulsion phase and another freefall phase, with several subcategories determined by their range, such as tactical ballistic missiles with a range of up to 300 kilometers, theater missiles, operational missiles with a range between 300 and 3,500 kilometers, short-range ballistic missiles up to 1,000 kilometers, medium-range ballistic missiles reaching between 1,000 and 3,500 kilometers, and the intercontinental ballistic missiles, without a doubt, the most powerful and feared among ballistic missiles. With a range of over 5,500 kilometers, they are primarily designed to carry nuclear warheads and can reach any point on the planet. In addition to these missiles, there are other widely used models such as air-to-air missiles, launched from aircraft to hit other aircraft, air-to-surface missiles, launched from aircraft against ground targets, anti-ship missiles designed to hit ships and vessels, anti-tank missiles used to destroy tanks and other armored vehicles, surface-to-air missiles used to intercept enemy missiles or aircraft. Now let's see how they are made. Everything starts inside a computer. Engineers receive from the Army, Navy, or Air Force a list of requirements: range, maximum payload weight, type of target, launch platform. Three-dimensional modeling software turns these numbers into a virtual shell. Next, simulation programs reproduce hundreds of hypothetical flights, measuring heating, vibrations, and aerodynamic forces. Discovering a flaw at this virtual stage saves millions of dollars and months of work down the line. When the design is approved, it becomes a set of detailed instructions. The thickness of each plate, the chemical composition of the propellant, the type of chip used in navigation. Only then do suppliers release coils of aeronautical aluminum, rolls of impregnated carbon fiber, bags of aluminum powder, and drums of oxidizer, as well as boxes with gyroscopes, processors, and sensors. Each batch arrives accompanied by reports. If the purity of the metal, the granulation of the powder, or the strength of the composite fabric is outside the standard, everything is sent back where it came from. Bodies designed to withstand the heat of ballistic re-entry still rely heavily on metal alloys. Curved plates are welded by friction. The part spins against another at high speed. The heat from the friction fuses the edges without completely melting the metal, creating a seam as strong as the original material. Afterwards, the body is scanned by ultrasound, which can detect imperfections smaller than the head of a pin. For cruise missiles, the obsession is weight reduction. Carbon fiber tapes are wound over a rotating mold in diagonal patterns, impregnated with epoxy resin, and cured inside autoclaves. The result is a lightweight, rigid, and almost seamless cylinder. Hypersonic pods, on the other hand, require exotic materials. Friction with the air can heat the outer skin above 2,000 degrees Celsius, a temperature that would melt aluminum in seconds. That's why they use carbon composites mixed with silicon carbide ceramic, which can maintain their shape even when red hot. Many components are 3D printed as a single piece to eliminate welds exposed to heat. In tactical ballistic missiles and in most strategic ones, the engine runs on solid fuel. The recipe is similar to cake batter. Synthetic rubber surrounds oxidizer particles, almost always ammonium perchlorate, and metallic aluminum powder, which acts as fuel, multiplying the energy released. For hypersonic and long-range ballistic missiles, the propellant can be liquid or hybrid. Cryogenic aluminum tanks, welded and inspected by X-ray, store oxidizer and fuel separately. Turbines, marvels of precision machining, spin at tens of thousands of revolutions per minute, injecting the liquids into the combustion chamber. While the hull and engine take shape, electronic boards travel along pick-and-place assembly lines, where robots position processors, accelerometers, and gyroscopes with micro-tweezers. Then circuits go through a heated reflow soldering tunnel, where each solder joint melts and solidifies again. To withstand radiation, chips are encapsulated in ceramic and receive filters that reduce failures caused by energetic particles from space. The explosive warhead varies according to the mission. Conventional warheads contain explosives shaped to fragment into small shrapnel that sweep across an area. Anti-armor models carry a hardened steel dart that penetrates concrete before detonating. If the warhead is nuclear, the assembly takes place in a restricted access area with limited teams and dual verification protocols. Each radiological module is kept in a shielded compartment, and the entire operation is filmed to create an audit trail. When the shell, engine, electronics, and warhead are ready, it's time to put them together. Controlled torque tools tighten connecting rings that align everything with an accuracy of tenths of a millimeter. Shielded cables connect sensors to the onboard computer. The shell then goes back for a battery of tests. If the missile is ballistic, it still goes to the radar signature laboratory, where antennas measure how much reflected energy it returns. For cruise missiles, there are extra tests for wing folding and deployment. The final stage seems simple, but it isn't. The casing receives anti-corrosion primer, heat-reflective polyurethane paint, and sealing varnish. Identification stripes follow the conventions of the North Atlantic Treaty Organization or the codes of the client country. The entire missile is placed in a pressurized container with inert gas, sealed with metal rings that indicate any tampering. RFID tags and holographic seals record the date, batch, and destination. And that was today's video. Don't forget to leave a like and subscribe to the channel.